Our next speaker is Gukov, who forgot to turn on the sound, so we can't actually hear you.
I believe.
It's not recording, you have been talking.
Oh, yes, that's right.
Okay, and his title is Hidden SL2Z Symmetry.
Right, hidden SL2Z symmetry and mirror symmetry. So two symmetries in one talk. As the title suggests, there will be kind of surprising symmetries or hidden symmetries. And as a result, so my job is to introduce you to this in 1 hour. And because it's not supposed to be a kind of talk where you sit and say, oh, I know what's going to happen, or I know where it comes from. At least to me, that's why it's hidden, that's why it's surprising. So I expect that if you're like me, to you it probably also will be surprising. And that's why details of many of the things that I won't say, you can find here. And you can also find here solutions to several homeworks, which I'll suggest along the way. So there'll be some exercises to do. So the goal of this talk is to introduce SL2Z action or SL2Z symmetry. And there will be, in fact, 3 SL2Z symmetries. So there will be SL2Z acting on some vector space V. There will be another SL2Z acting on another vector space V, which will have its own definition. And there will be a third action of SL2Z acting on yet another representation V. And the point will be that this V's will be constructed. So my goal is to describe each of these actions and relation between them. And the point is that these V's will be constructed out of standard tools of homological mirror symmetry. Or the framework where we'll find this SL2Z will be in a typical setting of homological mirror symmetry or mirror symmetry in general. Central problem, or one of the central tools in homological mirror symmetry, is computing homes between various objects, say B1 and B2, in either derived category of coherent sheaves or in the enhanced version of the Fukaya category, which is supposed to match the first one via homological mirror symmetry conjecture. So I'll call this objects in categories, and we can consider them in both Fukaya and in derived world of coherent sheaves in the setting of today's talk. So I'll call these objects B because in physics they're usually referred as branes, but B will stand for object in a category. And in 2 of these SL2Z actions, the space V will be constructed as a home between something. So in the first case, it will be home between B1H, or I'll call it maybe BH plus and minus. And in one of these cases, namely third one, it will be constructed as home between also 2 objects in typical setting of mirror symmetry, where these objects will be called BCC and B prime. This second SL2Z action will be different. It will be realized on space V, which will be spanned on components of U1 symmetry action. I'll call it U1 beta, following standard notations in the literature. So fixed point set. So the setup in all of these cases will involve target spaces which are Calabi-Yau manifolds of particular type that play an important role in mirror symmetry. all these calculations of Holmes is going to be child's play compared to real proofs of homological mirror symmetry that we want to achieve. This will always be some simple finite dimensional spaces. But again, what's surprising is that the spaces will enjoy action of SL to Z. And again, if you're like me, to you it will be surprising, at least in 2 cases. So this one will be a surprise. And this will be surprising. But this one won't, because SL to Z, in this case, will be realized as a nice, obvious symmetry of the target space, and the objects that I'll choose will enjoy this symmetry. So in that sense, if everything is invariant, not necessarily pointwise, under SL to Z, then Hom also should be invariant, and therefore it will be representation. So in this case, SL to Z action will be manifest. So it doesn't deserve the name hidden. But in the first 2 cases, it will be non-obvious, at least to me. And if you happen to see how to derive this SL to Z in much more obvious way in the first 2 cases, then we definitely should talk. So that's why I'm giving this talk, because the only way I know how to derive it is using some equivalences such as mirror symmetry, but not direct methods. Not direct methods within each construction. But if you see how to derive it directly, then definitely tell me, or if you see any hints or anything similar, please tell me and we should discuss this. So, that's right. So now to summarize, there will be out of 3 SL to Z's, 2 will be surprising and 1 manifest, and 2 will be realized as Holmes and 1 not. So that's a short summary of the results. And then in the rest of this hour, my job is to tell you explicitly what these objects are and what U1 symmetry I'm talking about. And then we're done. So at least after that, I define my problem and made the claim. But question, of course, why am I saying that there are 3 of them? And is there any relation? The answer is yes. But so if you allow me, I'll erase this. I need a little bit more space. So I'll make this announcement that last 2 talks of the day are on the 4th floor. And I apologize that Blackboard is too small. And I don't want to be like Fermat, so I try to give you more details. So I'll erase this. And I'll use the space which we just produced to make the following claim, that there is actually a relation between all these 3 SL to Z actions, which is also surprising. So there are surprises at 2 levels. First, that we have SL to Z acting in a world of homological mirror symmetry where I don't usually see SL to Z. And the second is that there are relations between them, and the relations are equally non-trivial. So this is higher level of surprise. And what are the relations? So just again, to put summary on the board, and in case if I run out of time, we can at least know the main statements, or can look more details over there. So relations are the following, that this vector space, in fact, claim is actually stronger, that this vector space is Grothendieck group of modular tensor category, and that's why it enjoys SL to Z action, because it's Grothendieck group of something which has modular in a title, namely MTC, associated to a certain 3 manifold, or in fact to any 3 manifold. And when you choose this M3 to be of the form circle cross Riemann surface, sigma, then claim is that you recover from first the second one. So relation between them becomes equivalence if 3 manifold is a Riemann surface cross S1. And then I'll show you that in certain instances, second and third are also related for a very large class of examples. So they're just equal, but again, equal in a highly non-trivial way, related by equivalences. So, but representations, spaces are going to be the same, and representations are going to be the same. Now, what do I mean by SL to Z representation? To me, it will be something extremely concrete. So to say that there is SL to Z action, I have to tell you, so all the spaces in my case will be finite dimensional, or in most of the cases that I'm going to consider. And to say that there is a SL2Z action means to provide a set of S and T matrices of the size which is dimension of this vector space, such that S squares to 1, or perhaps plus minus 1, and ST cubed also is 1. So this is of size n by n if dimension of this vector space is n. Well, plus minus 1. Actually, I'm going to allow both cases, and related statement here is that the notion of modular tensor category will not always be traditional modular tensor category, but somewhat relaxed a little bit sometimes. For example, I will allow non-unitary representations and modular tensor categories. Right, so for example, if I have time, I'll try to show you how to derive from something which is very homological, such as this, very concrete expression for this S and T matrices, and in some special cases, we may discover the whole family of 2, 2L plus 1 minimal models. By this I mean S and T matrices that appear in modular representations of characters of these minimal models or the corresponding tensor categories. For instance, so this is whole family labeled by number L, which is integer. So this L is non-negative integer. And simplest case when L is equal to 2, this is going to be a very famous Lee-Young model. And in this case, the representation is two-dimensional, so S and T matrices are very concretely 2 over square root of 5 minus sine of 2 pi over 5, sine of pi over 5, sine of pi over 5, sine of 2 pi over 5. So that's a 2 by 2 matrix. And T matrix is slightly simpler. It's diagonal, and here we have exponential of 11 pi I over 3. Oh, sorry, 30. Exponential of minus pi I over 30. 0, 0, and so on. So even if I messed up some of the values, the point is that you will aim to get something extremely concrete, such as matrix elements of these S and T matrices from the world of homological mirror symmetry. So that's the goal.
And
so
it's appeared in the first example.
No, this actually is, will appear in these two examples, which are equivalent. So the family where this relation holds is in fact exactly this family and several others. So, but it includes that. So again, if I run out of time, I gave you all the statements. I gave you the target, the goal. I may not get to it, depends on number of questions and how I'm doing on time. But basically the rest is to unpack some of the definitions, namely tell you what are these objects and what are the fixed point sets. And again, don't expect that I'll tell you much about derivation of this SL2Z. Originally it comes from physics, and mathematically would use several non-trivial equivalences. So actually I don't know simple explicit explanation of this SL2Z. That's why I'm saying that if you see how to get it, tell me. So it's not supposed to be obvious, but as a statement, it's supposed to be a checkable statement. And among other things, my job is to explain how to compute this S and T matrices, again, from world of homological mirror symmetry. So that's the claim, that's the goal. Are there any questions before we embark on the journey? Okay. Yeah.
So with these things that are presented by Hans, they'll be acted on by left and right by endomorphism, one thing and endomorphism the other. Does the SL2Z act compute with those?
I have no clue. That's a great question. I have no clue. In one of the cases, in this one, it will actually be super interesting, meaningful question to which I should know the answer, but don't. Okay, so I'll start with the first one, which is somewhat simpler, but again, all three of them are related by these chains of relations. And we'll try to explain. So here my goal is to explain what this BH are. In all of the three settings, so my goal is to say what the target space and the objects are. In all of the three settings, the target space will be moduli space of Higgs bundles. So I'll try to keep that blackboard at least for a while. So, given a choice of Riemann surface sigma and group G, you can define the moduli space of G Higgs bundles on sigma, possibly with various ramification points, tame ramification, wild ramification, and so on, as the set of pairs of A and phi, where A is a gauge connection on the holomorphic bundle, phi is section of canonical bundle, or rather square root tensored with a joint bundle of G, such that they satisfy Hitchin's equations. So there are three equations, or in particular complex structure, they look like two equations and one stability condition. But in any case, you can define set of such pairs satisfying nonlinear PDEs, modular conjugation or gauge transformation. Okay. So this will be the setting for all of these three cases. And why is it interesting? Because in part, these moduli spaces enjoy very nice kind of illustration of SYZ conjecture, where we think of dual mirror Calabi-Yau's fibered by tori. So this moduli space of Higgs bundles is a completely integrable algebraic system, such that its generic fibers are Liouville tori, and there is some mid-dimensional base. And if you perform this Fourier-Mukai transform on a generic fiber, you obtain what we normally would say a mirror Calabi-Yau, but in this case it turns out that if you have this fiber F and dualize it to fiber, I'll call it LF, then the result, this dual fibration, will also be moduli space of Higgs bundles on the same Riemann surface sigma, but for Langland's dual group, which I'll call LG. So this very fact is not going to be this Langland's duality, and this structure is not going to be terribly important to me, but it may perhaps be quite relevant to origin of some of these SL2Zs, even though I don't know how, and I won't focus on that. It depends on which complex structure. That's a great question. So this space is actually hyperkähler. It has three complex structures, I, J, and K, or other infinite family spanned by linear combinations of those, with Kähler forms omega I, omega J, omega K, and the fiber is holomorphic in what Nigel calls complex structure I in one of them. Huh? Well, what I mean is that it's a Fourier-Mukai transform. So I'm trying to illustrate, superimpose two pictures where original space is fibered by fibers F, and Fourier-Mukai transform takes us to a dual fibration of dual Liouville fibers over the same base. So base doesn't change, but fibers are fiber-wise dualized. So this is supposed to be my impressionistic illustration of SYZ duality, or well, this is hyperkähler case, so maybe that's what's confusing. So in both cases, there are both holomorphic Lagrangian submanifolds, in particular generic fibers are holomorphic in complex structure I. But again, this won't be terribly important, or this won't be important at all to me. So what will be important is the following. And by the way, any other questions so far? Feel free to ask at any point. Again, since I'm aiming for something hidden or surprising, there is no point for me not telling something that's supposed to be obvious, such as this structure, for instance. So I can tell you already a couple of useful facts about this space that will be crucial or important for us. So one is that in complex structure J, since I have it on a board, I can say that this space MH G sigma is equivalent to moduli space of complex flat connections where you complexify your group. If you started with SU2, then GC will be SL2C, flat connections on the same Riemann surface sigma. That's one useful fact that will be crucial for us. Second useful fact that will be crucial is that you can explore the structure of this fibration or moduli of Higgs bundles if you introduce a Morse function which is Hamiltonian for U1 action. That's the U1 action which I call U1 beta, and it does the following. It basically rotates the phase of the Higgs field. So this action is, it's holomorphic in complex structure I. So I wasn't planning to describe all the complex structures, but since I already have it on the board, it's holomorphic in complex structure I. And in fact, it's Hamiltonian with respect to symplectic form, holomorphic symplectic form, omega j plus I omega k. Sorry, it's no, that's not correct. What I mean to say is, it's Hamiltonian with respect to omega I, but it rotates this omega by the same phase. So yeah, I'll maybe say it later. But anyway, this action, which doesn't do anything to A, so A transforms just to itself, and phi rotates by a phase, is sometimes called Hitchin action, because Nigel used it to study topology of this moduli space of Higgs bundles. So claim is that fixed point set of this U1 symmetry are all compact. They form perhaps many different components, which we'll explore later, but I already defined for you the second statement. Claim is that space of components of the fixed point set, which a priori is very geometric, it's completely classical, it's classical geometry, has something to do with this L2Z. In particular, if you have, for example, 3 fixed points or 2 fixed points, you get 2 or 3 dimensional representation of SL2Z. So that's kind of surprising. Again, my goal will be to gradually unpack it as long as I have time. But for, no, in fact, it depends on each of these applications. So in all of them, G can be anything. In fact, let me fix once and for all, for the rest of the talk, G will always be SU2. So as an illustration, but it can be anything. But sigma will vary on 1, 2, and 3, depending on which case we're discussing. So in fact, in the first one, it's going to be absolutely arbitrary closed Riemann surface, no ramification.
That doesn't really matter.
About 2, it is believed to be a statement about any sigma, but it's being understood and tested in cases where it has some ramification points. So it will be, for some reason, simpler, the story will be simpler if you add punctures on Riemann surface. This is very similar, and I don't fully understand it, to how in certain cases, like in work on Fock and Goncharov and others, somehow you cannot make a statement for closed Riemann surfaces, but the moment you make a puncture or put this ramification, things simplify. So that's, to me, it feels like that kind of phenomenon, but again, it's believed that it should be extendable to all sigma. But that's a very speculative claim. Okay, any other questions?
So this view of one action it also acts on the base of the geometry, and the right is the base of right?
Correct, yes, yeah. Yeah. Correct. Exactly. So yeah, that if I get to that, I was in fact planning to use this U1 action basically rotates the base of the Hitchin fibration, so that all fixed points sit over the zero fiber, which is global nilpotent cone. Yeah. Yeah. You seem like you have a question.
No, I just think there is in the self-dual situation, there is an obvious SL2Z action on the complex variations of Hodge structure. So I just don't know if 2 is that action or it's something different.
Self-dual means?
If the group is GLN, for example.
Yes. Yeah.
So it's equal to its Langdon's dual.
Oh, so
then Chi generates an SL2Z acting on each Hitchin fiber, in particular.
it's going to be 1. It's going to be 1. Yeah. It's so what? Yeah, that's very interesting. What you're saying is actually above my pay grade, but I know what you're saying, and it's going to be a SL2Z of type 1. So that in this frame, you're absolutely right. So that's basically you're saying that S duality or Langland's duality is actually not just S binary transform; it's full of SL2Z. That's this one. Very cool. So Tony already anticipated half of the talk. So to him it's not surprising. I should remove this. That's great. That's what I was expecting. But it's a very deep statement, something that you should ask Tony after this lecture. And I can tell you in some cases, so it also varies, depends on the problem. So let's get to case 2 when we get to case 2. So. No. So far this was intro because it will be MH, and Mohammed asked a very great question, for which G and which sigma, and point is it will be underlying playground for us in each of the 3 cases, just for different choices of G and sigma. And my setting is definitely closest to your answer in full generality will be the way physicists use it in 4-dimensional gauge theory in Langlands and so on. So I'm not sure to what extent and how exactly it means treating stacky points and so on. In some cases I will be able to say more, but that's probably the most general thing I can say. In fact, that's another reason why I would hope that not only you tell me how SL2Z is supposed to act, but also how to phrase it in more mathematical framework. Okay. So let me explain 1, because that's probably the easiest. And for this, we're going to do the following. We'll say that we'll use this isomorphism between moduli spaces of Higgs bundles and complex flat connections to do this. We'll take a generic 3-manifold. I don't know, what 3-manifold you like? Poincare sphere, maybe? So you slice it with a Riemann surface. So that's going to be same sigma as so far in 2 pieces, which are handle bodies, meaning that half of the homology cycles of sigma collapse on one side, are trivial on one side, half of the other. So these are going to be handle bodies, and such decomposition of a 3-manifold is called a Higard splitting.
So it's the same sigma as in Hitchin system or on the right vector?
Yes, correct. So M3 is going to be the same M3 as there, and so this sigma is going to be not the same sigma. It's sigma relevant for first part, but the Hitchin moduli space will be the same. And you can ask the following question. So this answers for us a question, what are the complex flat connections, GC connections on sigma? So if you try to ask an analogous question about 3-manifold, you can reduce it to asking to the question about Riemann surface using this Higard decomposition. Why? Because if we associate to sigma the moduli space of complex flat connections on sigma and view this as this big space, then you can ask which flat connection on sigma can be extended either to the left or to the right. And obviously, flat connections on the entire 3-manifold will consist of intersection points. So as a result, so if you have two pieces, let me call them, I don't know, M3 plus and M3 minus, the spaces of complex flat connections on each piece will form generically, if you do generic slice, a mid-dimensional submanifold inside this Hitchin space. Huh? It's going to be mid-dimensional, half-dimensional submanifold. So what it means, and again, think about, for this example, think about toy case where G is U1. So we're talking about abelian connections. Because this is handle body, so only half of them will be extendable to one side, only half to the other side. And statement is that for non-abelian or any group G, in generic situation, exactly the same thing happens. So only half of the space of flat connections on a central surface can be expanded either to the left or to the right. So they form mid-dimensional submanifold. In each one forms a mid-dimensional submanifold. So pieces are such that this corresponds to the yellow. This corresponds, this gives the red. And if you want to count complex flat connections on a 3-manifold, again, 3-manifold can be generic, what you get is a picture like this. You can count it by counting intersection points of two objects. I'll call them Higard branes because they come from Higard decomposition. Which are holomorphic Lagrangian submanifolds in the Hitchin space, in the Hitchin system. So the holomorphic, for those of you who care, in complex structure J, and Lagrangian with respect to omega I and omega K. So our whole space is hyperkähler, and these are especially nice. They actually respect a lot of this structure. So picture that's drawn here is a good illustration of what happens for Poincare sphere, because Poincare sphere can be represented as genus 2 Higard decomposition, and it has exactly 3 flat SL2C connections, which can be deduced from 3 intersection points exactly as shown on the picture. So this is a kind of good illustration of what's going on. So now I'm ready to say a little bit more about what the space is in the first context. So this BH plus and BH minus are precisely these objects. So I made definition of 2 other things in my to-do list. So BH plus is here, BH minus is here, and these are holomorphic Lagrangian submanifolds defined by Higard decomposition of any 3-manifold. So 3-manifold can be anything. Now, therefore, when you compute home between them, you can compute it in several different ways. You can view this branes as either objects of derived category of coherent sheaves, now ideal sheaves associated with these submanifolds, or you can view them as objects in Fukaya category because, again, they're simultaneously holomorphic and Lagrangian for different structures. In any case, because the problem is such a nice and symmetric, there are no holomorphic disks, and even if you're doing calculation in the Fukaya category, everything reduces to counting intersection points. The only thing you have to ensure is that you're in a generic position. So what we're computing basically is Floer homology for complexified group, analog of instant-on Floer homology of 3-manifolds, which Floer did for SU2. So we're doing basically SL2C version of this. Okay? So since next talk is going to be about, will involve the word skein, I have to say that this thing is also believed as a module over C of Q to be the same as a skein module of 3-manifold M3 that we chose. And since Mohammed is in the audience, and he and Cyprian made very recent contribution to this. Of course not. Of course not. So they introduced, they try to set this up very carefully, and I apologize actually. So there are many people not in the audience. Oh boy, Lee, Boden, Curtis, and Sven Meinhardt, and others. So in fact, I should have mentioned everybody, but again, I'm honest. So Cyprian and Mohammed introduced homology theory HP for three manifolds, which carefully deals with this problem. And it's basically the same as either GC Floer homology or Skane module of the three manifold, except that, and perhaps Mohammed is one of the few people who cares, the difference is I have to add reducibles. So for example, in the case of Poincare sphere, their homology would be two-dimensional, and I want to throw in one extra point. But my point is that in whichever representation you like, what's completely non-obvious from either one of them, as far as I can tell, is that SL2Z acts. And moreover, the statement is that all of these groups, everything that's written on the board, so I'm dealing with case one now, are actually categorifiable. So this is Grothendieck group, again, of some modular tensor category associated to three manifold and G, such that these intersection points, they generate very trivial home from the viewpoint of homological mirror symmetry, but the point is that it's actually a shadow of a much richer structure that SL2Z acts, and not only that, that this is actually Grothendieck group of a whole tensor category associated to a three manifold. So that's the first non-trivial statement. Modular tensor category. So claim is that just like there is invariant of three manifolds, which is either this, or this, there is actually a stronger invariant, which is categorification of those. And again, as far as I know, it's non-obvious, so therefore that's good food for thought. And I think at this point I completed the definition of first item. Namely, I told you what these objects are, BH plus, BH minus, so I'm ready to move on.
Yeah, but are you able to enlighten us on what terms that now
I made a claim that it acts and that you can compute S and T matrices, but I want to do it in the end, if I get to that statement, by relating them in one special family. So I can do it here, but then I won't get time for other things. So it's just the way, yeah. So a very good question. In fact, indeed, that's the question I want to ask, especially.
What does this mean? Does it mean that there is an interpolation between cases 1, 2, and 3, and there is SL2Z that acts on the whole family? Or is it some...
Yeah, claim is that in certain cases, for example, if a three manifold is S1 cross Riemann surface, then you can re-express this SL2Z action in terms of Hitchin space for that Riemann surface. That's why there was a confusion. So there is actually a relation between them, and I'll do one calculation in the end if I get time to it. So and I was planning to do it in either 2 or 3, but in case where all of them are related. But question is, in all of them, very concrete question, not only we have to make a claim that SL2Z acts, I'm a concrete guy. I love to know how it acts. What are the S and T matrices? And how do we get the answer I showed you in the very beginning? For example, for Poincare sphere, it will be a three-dimensional representation. So goal is to ask, what are the S and T matrices for Poincare sphere? Again, I won't have time to give you details, but you're welcome to look at the papers and find the answer for Poincare sphere. It will be some three-dimensional representation of SL2Z.
In this father theory, in principle, it would be gradients on that vector space. Is there SL2Z action with respect to grading?
Which grading?
Grading by third.
Oh, you mean this grading? Everything is sitting in basically very trivial degree most of the time. So in that sense, I don't think there is anything terribly interesting there. I mean, it's homology localized in 1 degree most of the time. So that's another great question. So you're asking really great questions. How these structures commute with other things. And in many cases, I don't know, including this one. But I suspect your previous question was actually very deep and interesting. This one, I suspect, is probably somewhat boring because everything localizes in 1 degree most of the time.
Is there a quick and dirty way to say what the objects in this category are?
Yeah, so simple objects in this category are essentially complex flat connections. So for Poincare sphere, there will be 3 simple objects in this category.
Was the monoidal structure?
Yes, in this case.
What is the monoidal?
Oh, what is the monoidal structure? Okay, so that is one of the things that I refer to the paper. But these are great questions. So this I can answer, but just don't have time. Yeah, unlike questions whether it commutes with home BCC, things like that. Okay, so at least I defined for you the minimum promise was that I'll try to define for you all of the things which enter the board. I already defined U1B symmetry, or U1 beta, that's the Hitchens action. I defined B plus, B minus. So let me move on to 2 for a second and give you a concrete example or maybe a calculation, or at least half of the calculation. Depends on time. So I want to erase this one, clear this part. Yeah, so we're going to use the second fact that there is a U1 action on moduli space of Higgs bundles. And consider the following case. So we'll consider MH, which is that same setup of mirror symmetry where it applies to Langland's duality for G, which will be, again, SU2 for all of our discussion. Riemann surface will be for simplicity and only for simplicity. This can be generalized, although each case seems to be interesting, but they're all kind of similar. In such a way that I'll take genus 0 Riemann surface with 1 point of wild ramification. So this point will be wild ramification, and the families that have been looked at in detail where these S and T matrices have been computed involve either one such wild ramification or combination of wild and tame ramification, and slowly going to higher genus. That's where concrete computations have been done. So for me, I'll focus just on this case. And since there was a parameter L in the very beginning where we had this family of minimal models labeled by L, so there are S and T matrices. I'm speaking about Higgs bundles. So it depends on your point of view. In complex structure J, these are basically local systems or complex flat connections. Huh? Well, wild means, in either language, it means pole of high degree, high order pole. So you have a pole of arbitrary order. And tame means pole of first order. It's terminology which is meant to be analogous to wild and tame ramification number theoretic case of geometric Langlands, but it's not perfect. It's geometric version. So again, we're talking about SL2C or SU2 Higgs bundles. So all matrices will be of size 2 by 2. So we'll choose a pole of high degree, since it's supposed to be wild, such that it's 2 by 2 matrix times z to the power 2l minus 1 over 2 dz. So it's a pole of half integer degree. And it gives you a family of moduli spaces of Higgs bundles. So for example, in that baby case when L is equal to 2, MH is elliptic fibration. Its hyperkähler dimension is 1 with one singular fiber of Kodaira type 2. Okay.
Are you missing a minus there?
No, why?
Because it's a pole.
And?
Either I was negative or there is a minus in the pole.
Oh, yes. I'm definitely missing a minus, yes.
So that there is no other term in the lower ampere? You only have the kind.
Oh, sorry, this is the leading piece. Yeah, this is the leading piece, yes. So that's this L, which was labeling the family that I mentioned in the very beginning. So in all of these cases, you can say that this Hitchin space also happens to be some Coulomb branch of some mumbo jumbo, and that's actually where SL2Z comes from. So in this work with Nakajima and others that I raised, actually we use this in order to derive a SL2Z action, but I'll try to give you a more geometric summary of what's going on. And geometric summary is the following, that in these cases with wild ramification, what happens is that there is a very nice subgroup, Zn, sitting inside U1 beta, that actually fixes the hyperkähler structure of MH. This has to do with the fact that because of Stokes rays going out of this wild ramification point, or you can understand it in slightly different ways, the holomorphic structure, which I was trying to write in the beginning, normally would be rotated by, in the same way, e to the I theta times omega. So this is one of the combinations of omega j plus I omega k of the Hitchin fibration. And normally it would not be invariant under such symmetry, but something happens in the case with wild ramification that you get an extra factor of n here, which depends on how many Stokes rays are coming out of this point. For example, in this case, it will be something like 2L plus 1, actually, in this family. So n is equal to 2L plus 1. And because of that, if theta is nth root of, or e to the pi theta is nth root of unity, what happens is that there is a discrete subgroup Zn, which fixes not only Kähler structure, Kähler form omega I, but all the other ones. So it actually preserves all the hyperkähler structure. On MH, yeah. As such, in particular, this implies, among other things, that all the fixed points of this Zn symmetry will be isolated points, because they would have to be Lagrangian and symplectic at the same time. And a quick argument, again, for which I refer to the paper, says that all fixed points are isolated in this case. Okay? And then, if you're in such situation, then you can ask, how does your space, MH, looks near in the neighborhood of each fixed point? So maybe I'll stop going back and forth, but focus on this blackboard and erase the rest of it. So what we're aiming at is that SL2Z here will be acting on the vector space built on this fixed point, so as many as they are. And my goal is to say a little bit more concretely what this SL2Z action looks like. Zn fixed points. It also is easy to show that they actually coincide. So in this case, with U1 fixed points. So in this case, They coincide, but more importantly,
That's some very accidental situation. So
Correct.
the first thing you did was, so you don't have higher order terms in the Laurent table because you want your stock certification to be cyclically symmetric.
okay, so yeah.
Which is a condition. And now you're saying that they're only isolated fixed points because of this ZN symmetry. And you're going to show that there is an SO2Z action on the function space of these points?
Correct, correct, yes. So in general, what will happen is that some of these things which are much nicer in the present setting, namely that these are just points, will not be the case. That's why a statement which I raised had space spent on components of the fixed point set. So that was more general statement, and in the cases with wild ramification, that's indeed the picture. So this is somewhat simplified version. So what does MH look like? So suppose we have a fixed point. Yeah.
Your capital N is just the order of the pole?
My capital N, no, it's not order of the pole, it's number of Stokes rays. So N is 2L plus 1, and order of the, so it's related to order of the pole in some simple linear relation, which is contained in expressions on the board. So there is a fixed point, and at each of the fixed points we have the following geometric data. We have the value of the moment map with respect to complex structure I, because that's the one which again will generalize always, and this U1 Hitchens action is Hamiltonian with respect to complex structure I, or symplectic form omega I. So we have this moment maps, and also we have the weights which are telling us how this U1 action, or sometimes called C star action, acts on a normal bundle. So therefore there are weights W1, W2, and possibly so on, telling us the degrees. So in my baby case, when this is elliptic fibration, it's just hyperkähler dimension 1, so there are only two weights, W1, W2, to keep in mind. So it's interesting that the data, which I never thought of as kind of meaningful, to me these numbers, the weights for each fixed point and moment maps were quite random. But Dupay, who was studying this very actively and in great detail in the past 5 years or so, found some interesting structure underlying these numbers. So for instance, in our example, which has Lx equal to 2, there are exactly two fixed points. So the values of the moment map are 0 and 1/5. And the weights associated to each fixed point are 2/5 and 3/5, and 6/5 and minus 1/5. So there are two fixed points in this baby case when L is equal to 2. So based on what I said, you should expect that we get some two-dimensional representation of SL2Z. In fact, that's exactly the one I wrote in the very beginning with those S and T matrices. And the magic is that somehow these values of matrix elements, S and T, are contained in this purely classical geometric data of how U1 acts and in the neighborhood of each fixed point, or more generally component of the fixed point set.
So as Tony said, right, there's an SL2Z action by fiber-wise between.
Oh, that's a different one. That was in world 1. That was in first.
There's also one
But
here.
there's also one here, and so.
But that's not the one. So this SL2Z, in this case, it's not the one.
But yeah, finished. Can you tell us which weight spaces are the ones on which SL2Z are?
Well, it will be space spent on this it's two-dimensional space. So my job is to tell you a little bit about how these values are related to S and T matrices that I had in the very beginning. So general formula, general in the case of anything that involves wild ramification is this, or one of the facts, that you take a sum over, in general, components, or in this case, just fixed points of the following quantity. it's t to the power k times mu of a given fixed point. So let me give it a name, maybe s, mu of s. And then product of all the weights, 1 minus t to the w1, and so on, 1 minus t to the wn, where n is our dimension of complex dimension of mh. So n is dimension of mh.
So you're assuming now isoelectric.
Yeah. So let's indeed stay in this territory. So the claim is that this gives us not exactly elements of s and t directly, but it gives elements of s, t to the k, s in slots 0, k. Okay? So in other words, that just purely geometric data of moment maps and the weights gets translated into matrix elements of S and T somehow.
What does 0 k mean?
Matrix element in first row, or maybe I should say 1, k. It's particular matrix elements of these S and T matrices. And then in general, we give so this is something I can explain to undergraduates, but in general, we give a prescription how to construct all of the S and T matrices, all of the matrix elements. But again, I want to convey the surprise, at least to me, that there is any relation at all between something modular and
all the weights enter. It's not just incoming directions, not outgoing directions,
all of them, yes, yeah.
I mean, this sounds like something that you would get when trying to compute, the cohomology of powers of a pre-quantum line bundle by localization.
Correct. Yes. Yeah. So this formula is known as Hitchin character or equivalent Verlinde formula. It's integral over mh of exponential of k times omega I, wedge tot class of mh, computed equivalently with respect to U1 beta action. Exactly. That's what it is. So in fact, Konstantin here and many other people have worked on it. So in fact, Konstantin and Woodward in some sense started this. And again, it's kind of interesting that in that world, which now goes by the name either equivalent Verlinde formula or Hitchin character, because it's trying to compute character of kind of Hitchin moduli space, there is, and it can be localized indeed to the fixed point set, so that's precisely the reason. So there is equivariant characteristic class that you're integrating, and that's how you define this expression in general. That's why generalization exists. But the interesting thing is that it contains information about this S and T matrices. So to me, this is surprising. And I think I'm running out of time, so let me just finish this example, and unfortunately I won't go any further, but I don't want to abuse my time, and I just want to say that something extremely concrete and easy. So in this example, which is already on the board, so let me just finish with one equation to illustrate that it's very concrete and that we also take not only positive but negative directions. So you have two fixed points, so their moment maps are here on the board. So weights are also on the board. So the expression we get is t to the power, which is moment map, and for the first point it's 0, so it's going to be 1, divided by 1 minus t to the 2/5, 1 minus t to the 3/5. These are the weights of the first point, but the second point will have both pluses and minuses, and the second contribution is t to the k times moment map, which is over 5, and 1 minus t to the minus 1/5, and 1 minus t to the power 6/5. Okay. So that's what it is for this concrete example. So again, I apologize for running out of time, but everything can be made extremely concrete, and these components of fixed point sets were studied in gore detail. So there is a lot of concrete technology to compute them. But surprise is that there is a SL2Z behind it, that there are not just random numbers, not just values of moment map, but they actually encode something, and even more surprisingly, that there is a whole tensor category behind it, not just SL2Z, but its categorification.
K is the level?
Yes, K is the level.
The tensor structure, does it come from monoidal structure? Does it come from some convolution?
In this language, I don't know, actually. So for us, it came as a consequence of the fact that this Hitchin space is Coulomb branch of some theory, and this theory admits Donaldson-Witten type twist, which means that there is a three-dimensional TQFT, and according to Toraev's theorems, three-dimensional TQFTs are in one-to-one correspondence with modular tensor categories. So for us, this MTC and the calculations we actually do were not geometric, so they came from thinking about TQFTs. But it would be nice to formulate this in purely geometric language, which is what I try to do. So again, apologies for running over time.
It seems like we already started with questions, but first. Okay, more questions.
It seems like we already finished with questions too.
I think, yeah, we integrate the questions back. So thanks again, and you have 10 minutes to move upstairs. I think the usual.
Сразу не ухожу, но ухожу в 5 часов.